lot like the example given in your textbook about what it means to parameterize a curve. This is not exactly what it means, but it's really, really close. So I'm just going to go ahead and stick with this example. If I have the equation of a circle, x squared plus y squared equals 4, we know that that circle looks something like this. It's centered at the origin, it has a radius of 2, so it's going to look a little bit like this. My scale is way off there, but I hope you'll bear with me. This has a radius of 2. Now, this equation, this graph, fails the vertical line test. If I were to draw a vertical line anywhere through this circle, that line would pass through the circle twice. So this function right here, or this equation right here, is not a function. However, I can solve this equation for y. I'll start by subtracting x squared from both sides, and then take the square root of y. And that gives me plus or minus the square root of 4 minus x squared. Now, it's still not a function, because if I graph this, it's going to fail the vertical line test. If I graph this whole thing, that is. But if I take one of them and call it y equals positive the square root of 4 minus x squared, and the other one, y equals negative square root of 4 minus x squared, now I have two separate equations, and each one, individually, separately, will pass the vertical line test. That's a terrible circle. I hope you get the idea. That's not really what we're going to be doing in this section, but I did want to use that example as a way to get us started. What we're actually going to be doing is taking equations that would not normally be functions and finding a way to express them so that they will each individually be functions. Here's our first example, and this one is actually already a function, but bear with me. The process here is a little bit, well, I'll just call it interesting. So we're going to start with some simple cases. I want to split this up so that I have an idea of what just x is doing and an idea of what just y is doing, but at the same time. So I'm going to assign a parameter. And to make the simplest case, there's almost always a simplest case like this where I can just take the x and reassign it. So let x equal t. That's your easiest parameterization. And that makes x a function of t and y a function of t. But if x is just t, then y is 3t squared plus 3. And this is what we call a system of parametric equations. T is the parameter. Now, I know how to graph this. It's just a quadratic that's been stretched and then moved up 3 units. It would look something like that. That's a terrible, terrible parameter. Let me try one more time. There, that's a little bit better parabola. And of course, that continues. This one, though, although it'll have the same shape when I'm done, we can go about this a very different way. Graph these. We're not going to spend a lot of time on that in this video. But if I know what t is, then I can determine what both x and y are. So let's go t equals 0. That means x is going to be 0, because at least in this case, t is just x, right? But y is going to be 3 times 0 squared plus 3. When t equals 1, x also equals 1, and 3t squared plus 3 equals 6. I'll do one more. When t equals 2, x also equals 2, and y equals 2 squared is 4 times 3 is 12, plus 3 is 15. If I graph these points, I get, now what I'm graphing here is x, y, right? So I'm going to have 0, 3, 1, 6, and 2, 15. That's up here somewhere. And what's happening here, I'm going to try that graph again. What's happening here that's different is that I set the first time parameter, the starting point, essentially, to 0. And so my graph starts here, and goes in this direction. When I graphed this one, I happened to graph, starting from here, I graphed up, and then I went back to here and graphed up the other side. With this one, I have to start here because that's when my time parameter starts. That's my smallest t value. I'm going to start here, and I'm going to follow these values. So I'm going to go take these points rather, in order and go up this way. And in this case, I'm going to stop here. I'm not going to put an arrow down. All right, we'll talk more about graphing later, but I wanted you to see that although you end up with the same graph, depending on what your t values are, there may be some differences. Something really cool about parametric equations is that they're not unique. I'm going to come up with a completely different set of parametric equations for this same equation here, the same function. I think I'll do this over here on the side. If I let x of t equal the square root of t, and y of t equal 3t plus 3, but at the same time, my table of values would look something like this. I'm still going to let t, oops, my t, this is my x, this is my y. I'm still going to let t equal 0 and 1, but then I'm going to skip to 4 because primarily it's easier to take the square root of 4 than it is to take the square root of 2. Magic will happen when I do this though, because the square root of 0 is 0. So t equals 0 means x also equals 0. And when t equals 0, I get 0 plus 3, which is 3. Note that that's the same value I got here, the same point I got here. When t equals 1, I get the square root of 1, which is 1, and 3 times 1 plus 3, which is 6. Again, the same point as I got down here. Now, when t equals 4, I get the square root of t. That's 2, sorry, the square root of 4. And 3 times 4 plus 3 is 15. So even though I had a different t value here, I got the same point as I did down here. And that's one of the things about parametric equations that makes them so interesting and so useful. They're not unique. You can find multiple ways to parameterize a curve. I've always had trouble saying that word, by the way. Parameterize. A lot of people say parameterize. I don't know. Whatever. There are multiple ways to do it, right? I'm sure there are others. These are the ones that kind of come to the top of my head. This one is what I would call the trivial case. Just letting x equal t, it's kind of cheating in a way. Because, yeah, you end up with parametric equations, but, I mean, really, that's just 3x squared plus 3 with t instead of an x, right? It's a little bit too easy. This one's a bit more interesting. But there are more than one. So I think that's an interesting thing, interesting observation to make. Something else that's really useful about parametric equations is that they can model specific situations. This is example 3 from your textbook. Notice that it says an object travels at a steady rate along a straight path. That tells me this is a straight line, right? Between -5, 3 to 3, -1. So on grid, on a Cartesian grid, we have -5, 3, and 3, -1. So frankly, we could just take this information, right, and find the equation of the line that goes between these 2 points. So what do we need parametric equations for? Parametric equations give us a lot more information than just the equation of the line. Very quickly, I know that the slope of the line is going to be 3 minus -1 over -5 minus 3, which is 4 over -8. So that's -1/2. And so the equation of the line is y equals -1/2 x plus some value b. All right, if x is, let's see, we'll use the 3, 1 point. If x is 3, y is -1 at that point. So I'm going to have -1 equals -3/2 plus b, adding 3/2 to both sides, that's adding 1.5 to both sides. You get 1/2 equals b. So the equation is y equals -1/2 x plus 1/2. That's the equation of this line, but I don't know where it started, not from the equation. And I don't know which direction the point was going in. All I know is that this line, with or without its, if I don't necessarily have the points on the line, all I know is the line, right? Clearly my graph is very approximate. My y-intercept should be at a half, not at 0. But the point I'm trying to make is that this equation doesn't tell me as much as it could. If all I have is the equation of the line, or even a graph of a line, I don't know where I started or what direction I was going in. With parametric equations, though, I can find that information. So let's see if we can find a way to write a pair of parametric equations for this line, given this information, given the 2 points, the amount of time it was traveling, the distance, the measurement in meters, and all that stuff. I'm going to start by creating a new version of the graph. I have the points -5, 3, which is about there, and 3, -1, which is about there. And I know that I'm starting at -5, 3. It's going from -5, 3 to 3, -1. So I'm going in this direction. One of the things in the equation that we haven't even talked about really yet is that it takes 4 seconds to make this trip. There's a point or an object, they're calling it an object, that's doing this, right? That's making this journey, if you will. It's starting here and it's going here, but it's taking that trip in 4 seconds. So just in terms of x, because this is how we do this, x of t, we can say that we have to go from -5 all the way to 3, and we're going to do that in 4 seconds. That means we're going to be traveling a certain distance over a certain amount of time, and that's a rate. So we're going to be traveling from -5 to 3, and one way to determine what that distance is you start at the end and subtract the first number. So 3 minus -5. 3 minus -5 meters, because we're told that the distance is measured in meters, or the coordinates are measured in meters. That means that this -5 here means that we're back 5 meters from the origin. So we're going to travel this total distance of 8 meters, and we're going to do that in 4 seconds. Meters per second. That's a rate. Now, I have 8 over 4, which is 2, so I'm traveling at 2 meters per second in the x direction. Let's see what's going on in the y direction. Y of t. I'm not actually writing the functions here. I'm just kind of getting an idea of what the situation is. Let me highlight. See, I'll use blue for x, and then I'll work out what y is. In the y direction, we're going from -1 up to 4. Actually, we're not. We're going from, sorry, that's 3, not 4. We're going from 3 down to -1. So you start at the end and subtract. -1 minus 3, and that's also going to be over 4. And that's also going to be in meters per second. So I have -4 over 4, which is -1 meter per second. And that's also a rate. I'll highlight that one in green. So when this object starts moving, it's here, and when it finishes moving, it's here. So often the parameter t represents time. Very, very often, in fact, the majority of the time. Not always, but the vast majority. So when t equals 0, in other words, when this thing starts moving, it's at this position here. So if we know what the rate is another word for slope, right? This is a change in y versus a change in x. This is a change in meters versus a change in seconds. So when seconds is 0, when time is 0, we're going to have the x coordinate at the point, at the address, if you will, at the location, -5. So since the rate, I want to put a line in here, since the rate is 2 meters per second, that's my slope, that's my change in distance over time, and I can write this as sort of as the equation of a line, the slope times the variable, plus or minus the y-intercept, but it's not really a y-intercept in this case. What I'm looking for is what happens, or where are we here, just in terms of x, when t equals 0? And the answer is that we're at -5. So if I were to plug in 0 right now, I would just get, when time is 0, this would be 0. And I need to adjust that so that it's 0 minus 5. Now I can look at this and say, for x only, when t is 0, x is at -5. When the time starts for this thing, the x position of the object is -5. So this is the x equation of our pair of parametric equations. Let me go ahead and highlight that, and I'll do it in blue since it matches the slope for that one, the rate. Now the rate for the y equation was -1. So for x, we're going from left to right. That's a positive direction. For y, we're going from the top down. That's a negative direction. So it makes sense that the so-called slope here, the rate of change for x, would be positive, and the rate of change for y would be negative. All right, now, so again, I can write my equation, y of t equals -1 times the variable. That's kind of like saying y equals mx plus b, right? Y equals m, that's my slope, which is a rate of change, times the variable, plus or minus some constant. Now, in this case, I want to know what happens again when t equals 0. So right now, if I plugged a 0 in here, I'd get y equals 0. So I need to adjust that because actually, at time equals 0, y equals 3. So I'm going to say plus 3. And that is my y equation for the pair of parametric equations. It's not the only one. This is not the only pair of parametric equations. As we talked about previously, these are not unique, but this is one way to find this information. Now, I'd like to point out something else here. The slope in a standard line where you don't know starting point or direction, you just have the equation and so you can plot the line. From this equation, you could find some points and you might be able to find these points. I think other points might be easier to find. But for the parametric equations, we are given these specific points because they are the starting and ending points of the path of the object. So now I can write x of t equals 2t, sorry, not plus, but minus 5, and y of t equals -1t, or just negative t, plus 3, and that is my system of parametric equations. But let's make an observation. The rate in just the x direction was 2. The rate of change of position in just the y direction was -1. The rate of change overall is -1/2. But that kind of makes sense, because if you look at just the rates, the slope of this line is the change in y over the change in x. That's -1/2. And that's what slope is. These are not -1/2 because these are the changes in distance over time just in the x direction and just in the y direction. All right, let's test our parametric equations and see if they give us this information. So at t equals 0, I should be at -5, 3. And we actually built these equations so that that would happen, so it really should work. When t equals 0 here, I get 0 minus 5, which is 0. So at t equals 0, x is -5. And at t equals 0, I get -0, which isn't really a thing, plus 3. So when t equals 0, y equals 3. And that's here. So I'll have a point here. Now, I also want to know what happens at, say, t equals 1 or t equals 2. So I'm going to grab another point. I'm going to grab another point in time. Let's see what happens when t equals 1. At t equals 1, I'm going to have 2 times 1, which is 2, minus 5, which is -3. But that's just the x coordinate. For y, when t equals 1, I'm going to have -1 plus 3, and that's 2. So I should have a point at -3, 2, which is about there. When t equals 2, I don't have room for a whole lot of these, but I'm going to do this one and one more. When t equals 2, I have 2 times 2, which is 4. 4 minus 5 is negative 1. And for y, when t equals 2, I get negative 2 plus 3, which is 1. So I should have a point at negative 1, 1. And that is about there. So far what's happening is I've been able to find some points on this line. And if I'd been given this equation, I'd be able to do the same thing. If I plug a negative 1 in here, I'm going to get a negative 1/2 times a negative 1, which is positive 1/2. And positive 1/2 plus positive 1/2 is 1. So when x equals negative 1, y equals 1. And there's that point right there. The thing is, I don't know when that occurred with just using this equation. Using parametric equations, I know that that's the position of this object after 2 seconds. And that's important information. All right, I'm going to do one more, and I'm going to skip to 4. And the reason for that, that's t equals 4. The reason for that is that we did this, made this journey, traveled down this line in 4 seconds. So I know what happened at t equals 0. I didn't record it, but when t equals 0, I get 0 minus 5, which is negative 5, and 0 plus 3, which is 3. So negative 5, 3 is here. And I want to see also what happens at t equals 4. So when t equals 4, I get 2 times t, which is 8. 2 times 4, which is 8, sorry. And 8 minus 5 is 3. So when t equals 4, x equals 3. And for y, when t equals 4, I get negative 4 plus 3, which is negative 1. So I should have a point on the line 3, negative 1. Well, I most certainly should have a point on the line 3, negative 1, because they give me that point. They also give me the point negative 5, 3, so that point should certainly be on the line. The difference between graphing this line, even if you know these 2 points, and graphing the parametric equations using this information is that we know not only what the line looks like, but where you started and where you finished. So using the parametric equations version of this line, I want to erase, and I can't because I'm using a line here instead of a hand-drawing pen. So I'm going to remove the line instead and replace it with a different one. And the line I'm going to replace it with, and I'll just stick with white, is the one represented by this table or by these equations. And that is the line, specifically the line segment, that starts at the point negative 5, 3 and ends at the point 3, negative 1. In addition to that, because I'm using parametric equations, I know that when t equals 0 is where I start, that's this point here, and that t equals 4 is where I end, that's this point here. I can include in the graph an arrow or 2 or 3 to help the viewer recognize the starting and ending points and therefore the direction. Okay, this video is a little bit longer than I intended, but it's a really good, I think, introduction into what parametric equations are and how to take information that you might normally just use to create a static equation of a line, like the one we have here, and turn it into a more informative version of that information. This line tells me a lot more. This diagram here tells me a lot more than the previous one. So while in this subsection, we learned how to go from this type of information, standard static information, standard static equation of a line, into parametric equations. In the next video, we're going to learn how to eliminate the parameter, which means we're going to go from this form of an equation or this form of information back into this form. So that's all I'm going to do for this video, and I'll see you in the next one.